In this video, we're going to quickly revise a summary of the organic chemistry you learnt in level 2 and use this as a basis for going forward in level 3. There are more videos that you can watch if you need to brush up on a particular type of reaction, and they will be found on Edpuzzle as well, but otherwise this is a good place to start. And we want to get this done so we can, in the next couple of weeks, focus on the new organic chemistry. So the basics. Before we go any further, we've got to remember what we learnt last year about carbons and how we name them. So this is really important, this table here, where we learn the different names for the different numbers of carbons in a chain. So you need to memorize this again. I'm sure it's locked away, but 1 equals meth, eth for 2, etc. And then if they're used as a branch, then we use methyl, ethyl, propyl, butyl, pentyl, hexyl, etc. And that becomes useful because we will use these branch names also when we name things such as esters or amides. So it'll come back to us. So make sure you revise that. And the functional groups we learnt last year, here are the suffixes as well for them, and alkane is always ane, and then we have the ene for alkene, ine for alkyne, enamine for amines, enol for alcohols, and noic acid for carboxylic acids. And the only prefix we have is for haloalkanes, where we had like the halo, such as bromo, fluoro, etc. And see those X's in there? That tells us that we need to put our number. We need to number where it is, tell us where that halogen is or where that double bond is in the molecule. Now the rules. We need to make sure that when we are naming or drawing, we follow these rules. In our naming, we need to make sure we give the lowest numbering possible. So we count from either side, that will give us the lowest number. If we've got more than one group, we use di, tri, tetra example. So if we've got two bromines, that'll be like dibromo. And if we've got multiple functional groups, we try to arrange them in alphabetical order. So that's the basics for our naming from last year. After learning about how to name things, we also learned about isomers. And we got 2 types of isomers from last year: structural isomers, which have the same molecular formula but have different arrangement or bonding of the atoms. That could just be moving a functional group around, or it could be changing the functional group altogether. We also learned about classification for the haloalkanes and alcohols. We've got primary, if the carbon attached to those groups is attached to 1 carbon, secondary 2, and tertiary 3. It's slightly different when we're talking about amines and amides later. You'll learn about that when you watch the video about naming amines and amides. The other isomerization is geometric isomers, and how for them to occur we need a carbon-to-carbon double bond that restricts the rotation around it, and that each carbon of that double bond has 2 different atoms or groups attached. So this one here, so but-1ene, you can see although there is a double bond that restricts rotation, this carbon has 2 hydrogens, so therefore this does not have geometric isomers. However, if we move the double bond across, then we've got but-2ene, and we can see that we can arrange the groups on the same side cis, so hydrogens same side here, or we can have them opposite where it's trans. General properties of the organic molecules: where that is the carbon chain increased, the strength of the forces holding them together, those intermolecular forces, increased, and the melting points and boiling points increased. Now you can explain why. After learning about this in 3.4, this is due because of the increase in the number of electrons, increasing polarizability of that cloud, creating stronger temporary dipole-dipole attractions. There are polar molecules, however, like alcohols and amines and carboxylic acids, and those are soluble in water and tend to have higher melting points and boiling points because they've got the permanent dipole-dipole interactions or hydrogen bonding. But the alkanes and alkenes and alkynes, they are not as strong and polar, and are not soluble in water, forming two layers with the organic layer generally on top. And the other properties, amines were basic, so we can use red litmus paper to detect them because it will turn blue, whereas carboxylic acids will turn damp blue, litmus paper red. Now this is the chart that probably overwhelmed you perhaps last year. That kind of shows together all the different transformations of the different groups. You see the alkenes in the middle has the most groups coming off it, can do the most transformations, make the most things. And I've kind of color coded the arrows where the purples are substitution reactions. We have eliminations in blue, green are additions, and we have oxidations in red. So remind ourselves that addition reactions, what are they? It's when you break the double bond of the carbon-to-carbon double bond to form two new single bonds to the added groups or atoms. So we can add hydrogen with a platinum catalyst, it's an alkene to alkane. We can add two halogens like Br2, Cl2 to make a haloalkane. We can add a hydrogen halide such as HBr, HCl, will also make a haloalkane. We can add water across the double bond if we've got some acid there to catalyze it, and that makes an alcohol. Or you can make a polymer by reacting the monomer alkenes together. That's an addition polymerization. The two before that, remind ourselves that if we've got a alkene that's not symmetrical, that isn't the same on both sides, we only get two products. And the one that is the major product involves the carbon in the double bond with more hydrogens gaining the hydrogen in the major product, and that's what we mean by the rich getting richer, and the carbon will get the other one in the minor product. So that was addition. Substitution, that was simply swapping one group for another, so we can swap an alcohol for a chlorine group with Socyl 2, Pickle 3 or Pickle 5, haloalkane. Haloalkane can go back to an alcohol with aqueous, careful, aqueous hydroxide. We can swap the haloalkane for an amine using concentrated ammonia, or we could also use substitution to convert an alkane to haloalkane as long as we have UV light to catalyze it. And this is a slow reaction compared to the addition reaction talked about previous. Elimination, this is going backwards, the opposite of addition. It's where you break the single bonds to a hydrogen and another group on adjacent or neighboring carbon atoms and forming a double bond between them. So we can eliminate a alcohol group to form an alkene, or we can eliminate a haloalkane to make an alkene. Concentrated sulfuric acid with heat for alcohols and KOH or hydroxide and alcohol, key alcohol with heat for the haloalkane. And again, this is where we can get the phrase the poor get poorer. If the alcohol or the haloalkane is not symmetrical or asymmetrical, then you're going to get two products, and the double bonds will form between the carbon with the group that's leaving and the next door carbon with a fewer number of hydrogens attached to it. That will be the major product, and the double bond will form with the other carbon, neighbouring carbon, and the minor product. So that's weird to explain last year. Oxidation, that's where we basically detect it by increasing number of bonds to oxygen. So if we go from the alcohol group to the carboxylic acid, where we add double bond to the oxygen, and we could do that with permanganate, going purple to colourless with heat and acid, or dichromate, going from orange to green with some heat. The other one was when we use aqueous permanganate without acid, and that converts the alkene to the alcohol, but with two alcohols, one on each of the carbons. You'll still see the same change in colour. Other reactions we learned about was we learned that the carboxylic acids were acids. They behave like acids. They deprotonate in water. They're weak acids. They react with metals and bases, neutralize, and they form ions like that are called anoates. So this one here is the ethanoate ion. Amines are bases. They neutralize acids, and they form ammonium ions. So this is a methyl ammonium ion as it reacts with water. And again, it's a weak base, amines are, so that's why we've got this arrow there. It's the full reaction. Some final things to think about we learnt is that we need to be able to distinguish or determine unknown organics. If they generally are liquids, they're generally colourless. How could we distinguish them? Bromine water was a classic one. If we add that, it would turn from orange to colourless quickly with alkenes, but slow with alkanes. And you'd only work with UV light. Carboxylic acids produce carbon dioxide with carbonates or hydrogen carbonates, as well as turning blue litmus red. And you could also look at whether they are dissolved in water or not. Alcohols, carboxylic acids, amines will for small chains, whereas the alkanes, haloalkanes, and alkenes and alkynes will not. So those are what you also need to be able to use and explain. So that's the summary in bit over 12 minutes, all that you learnt on organic chemistry. And again, if something's not that familiar and you're struggling with some of that revision work, do go back and watch those videos from last year.